Hey, this is Dr. B, and let's have a look at organic chemistry, which is the study of carbon-based substances. We'll look at what they are, their bonding patterns, how we can draw them, some of the common functional groups, and some typical chemical reactions. Let's begin by checking out four of the most common elements used in organic chemistry. We have to include carbon, but if we also include hydrogen, oxygen, and nitrogen, we've covered the vast majority of organic substances and what's present in over 95% of our own bodies. They have a simple bonding pattern. Hydrogen tends to form one bond, oxygen two, nitrogen three, and carbon four. Honk if you love chemistry. Knowing that, we can look at these substances and consider whether they're reasonable or not. Take a look at that substance known as methanol, and you'll realize that fine, every hydrogen has one bond, the oxygen has two, and carbon does have four. This, however, is incorrect. We should only have four bonds on carbon. How's that one look to you? Should be fine. That's propanol. Ethanol looks fine. Yikes! Well, I'll let you go through that, but there's a nitrogen, 3 bonds. There's a nitrogen, 3 bonds. There's a carbon, 4 bonds. This entire molecule is reasonable. This one, not so much. I see 5 bonds on that carbon. So, in both cases, those happen to be what they call pentavalent carbons. We can divide up these substances into primary, secondary, and tertiary sections on them. Let's take a molecule such as this, since this has all 4. Starting here, these are primary alkyl groups in this case, since they have 3 hydrogens on it. They're only mono-substituted. That one is tetra-substituted, no hydrogens at all. We call that quaternary. Notice it doesn't have an R. Work your way around the horn. That should be secondary, 2 substituents. That's tertiary. How about that one? Primary. Here, secondary, secondary, and secondary. We can do the same thing for amines. That one's only mono-substituted, so primary, secondary, tertiary, and we can add an additional alkyl group in this case, making this a quaternary ammonium salt. And once you have a formal charge like that, well, if that was, say, tetramethyl ammonium chloride, you need anion to go with it, that would then be a water-soluble salt, bringing you into the water layer and out of that greasy organic layer. We could draw molecules lots of different ways. Let's use ethanol and draw it about, 8 different ways. There it is, using perhaps one of the most informative methods. We call that a plain old structural formula. It shows every bond. If we do it this way, it's much faster, but it's a little harder sometimes for students to interpret. We call that a skeletal formula. This does not have any hydrogens, unless occasionally you just want to show a functional group. But every bend, like up here, or end, like there, implies a certain number of hydrogens. Can you see how we have to have 3 hydrogens on this beginning carbon? We have to have 2 on that one. These are skeletal formulas. They're super fast, and they are the go-to method once you get used to them. If we just draw something like that, all it is a molecular formula. It's very ambiguous oftentimes. For instance, there's 2 structural formulas that fit this, right? We can, if you're in a hurry, you might like this method. It's like typing it out on a computer. We call it a condensed formula. And maybe even more informative than a structural formula is a stereochemical formula, where you actually show not only every bond explicitly, but in 3 dimensions. Wedges means coming out at you. Hatches, which are a little hard to see, dots like this, mean going into the plane of the board. And on a computer, you may see these types of molecular models that are ball and stick ones. They might rotate around. Or you might see a space-filling model trying to give you an idea of what it really looks like with electron density poured in there. And perhaps someday you'll see an actual microscopic image. But kind of an exciting opportunity is that, to my knowledge, that does not exist yet. I believe this will be something you'll see more of in the future and could replace a lot of spectroscopic techniques. What's better than looking at the molecule directly? And that's been done for some substances only within the last few years. That's penicillin. Okay, let's continue with some functional groups. Here they are. You tell me what they're called. In a typical organic chemistry course, you might have a chapter devoted to each one of these. Okay, those are alkanes. Those are alkenes, and those are alkynes. Notice it's alphabetical. These can render you unconscious. We call them ethers. These can render you inebriated. We call those alcohols. These ones oftentimes smell horrible, like rotten fish. Amines. Notice that's a primary amine. These may be used as an embalming fluid in some cases. These are aldehydes. There's a hydrogen right there. That means it has a terminal carbonyl group. A carbonyl group is present in the rest of these functional groups. It's a C double bond O group. So terminal means aldehyde. If it's in the middle, we call it a ketone. These can smell nice. We call them esters. Notice that that's not a hydrogen on that oxygen. That's another alkyl group. These are not amines. We call them amides. And if it is a hydrogen there, that's an acidic hydrogen, and we call those carboxylic acids. This is an introduction to organic chemistry.